Hi, welcome back. In this video, we're going to investigate how magnetic fields behave at the interface of two different magnetic materials. And when we do this, we'll be able to calculate or figure out the behavior of the magnetic field in one material given the magnetic field or the behavior of that field in the other material. We will also be able to derive Snell's law for refraction of magnetic flux. So let us take a look. Now in my drawing, I have an interface here which is the straight line, and it does not need to be straight, by the way. It can be curved, but if it's curved, then it can be approximated as straight locally, right? That's the idea behind calculus. Anyway, so I've just drawn it straight, and then we'll call this material 1 up here, and I'm going to say that it has a relative permeability of mu1, and we'll call this material 2 down here relative permeability of mu2. And so I've got, let's say, a B field coming in material 2 and maybe leaving material 1. Here's my B field. Call that B2 and B1 respectively. And these guys have tangential components, that is, a component that is tangent to the interface. And so this guy would be something like this, right? Parallel to the interface. So we'll call that B2T. And then it also has, of course, a normal component, a component that is normal to the interface. We'll call that B2N. And same with this guy. This guy has a component that should be parallel, by the way, not very well drawn. We'll call that B1 tangential, and then B1 normal, like this. Okay, and so the idea is to figure out the relationship between those, essentially just B2 and B1, the relationship as the magnetic field passes through this interface. Okay, so to do that, we're going to start with Gauss's law for magnetism, and I'm going to choose a Gaussian surface that's a cylinder. That's normal to the surface. So there's my Gaussian surface, and maybe it has a circular, a top and bottom area. We'll call that delta S, and then it has a height. We'll call that H. Right, and it's centered, so there's H over 2 on both sides. Right, and so this thing goes through the surface. Right, this is like a three-dimensional idea. So the surface is not a line. The surface is actually a plane. We're just looking at the plane head-on. Now, Gauss's law for magnetism, remember, there are no magnetic monopoles. So there's no way that this thing is enclosing any, net magnetic charge, whatever that means. So we're going to say that that's equal to 0, right? And so when I look at the flux, the flux that passes through this thing, well, the normal components, I'll have B1N times delta S. So B1N, because that's the normal component, leaves the surface, leaving is positive flux, and I have negative because it's entering B2N times delta S, because the normal component enters, and the side of this cylinder, the tangential part, there's actually the normal parts. The normal parts are parallel now to the sides, and so nothing goes through there. And then the tangential part, anything that enters the tangential part also leaves. The tangential part of B, anything that enters the cylinder also leaves the cylinder, so that's got a net of 0, and same thing on this side, that has a net of 0. So this is all I need here for Gauss's law, and so this is equal to 0, and what I find then after I cancel out delta S is that B1N equals B2N. So this is to say that the normal component of B remains unchanged at the boundary B1n, and we'll just put the vector on there now. It remains unchanged, and so what we would say is that the normal component of B is continuous at the boundary since it does not change. Now, because the magnetic flux density is equal to the magnetic field intensity like this, and we've got this, we see that the relationship between the H's, the magnetic field intensity, is given by this. And so the magnetic field intensity H does undergo some change at the boundary, and so what we would say is that the normal component of the magnetic field intensity is discontinuous. Okay, now let's talk about our initial problem was related to the magnetic flux density B. So let's try to get the tangential component now of B. How does that change, if at all? Now, we're going to assume a general case here, and maybe the interface is carrying current on the surface. So let's just say, for sake of argument, that the current is going into the page, though it could be going out of the page as well, but it's on the interface, so it's either one of those two things. If it was, it would not affect our Gaussian surface though, because we didn't have to talk about the charge or the current that our surface contains at all. But now we're going to apply Ampere's law to get the tangential relationship of the B field, and so the Ampere's law uses the it relates a closed line integral to the current that it contains. So now we have to account for, hey, does this interface contain any current? So Ampere's law says this: the circulation of H around any closed loop is equal to the current that it contains, or the current that passes through that loop, right? And so what I'm going to construct, I can construct whatever loop I want, but I'm going to choose one strategically, like this here. And by the way, the current goes, there's current over here too. I mean, the current doesn't stop, right? But this is the path that I'm going to choose. All right, and we'll go up, and we'll go right, down, left, like this. And we'll say our path has a height of h, right, and a width of w, like this. Okay, so now when I evaluate this closed line integral, I have the following. I have h1n plus h2n times h over 2. So that would be from this side here. H1n is in the same direction as B1n, so that's up for h over 2. And so down here I also have up for h over 2. Right? So this entire thing is this segment here. Now then we go to the right, and so I have the parallel component, because of the dot product. The parallel component is now h1t. h1t times w is the length. So I add to that h1t times w. So now I've taken care of this segment. Now I come down, and so this is actually going to be minus, because I'm going down against the fields, h1n plus h2n times h over 2. So that takes care of this. And then again, I'm going against the tangential components here. And so this is going to be minus h2t times w, right? h2, because I'm in material 2 there. And then according to Ampere's law, that's equal to the amount of current that this thing contains if we say that this has a surface charge density of k, then it contains k times w. current. All right, so we have some things that cancel. We could also take the limit as h goes to 0 because we want to know how does this behave, this system behave at the surface. So we could take h go to 0, but we do have some cancellation as well. So what we end up finding is that h1t minus h2t equals k, because I can cancel a w then. Now, so that's the general case. Now in the absence of surface current, so now let's say our interface does not contain any current. We're not pumping any current through this thing. It's just maybe you know, the interface between air and an iron block maybe, and there's no current through the iron or something like that. So if in the absence of a surface current, and now this is a more specific but still common case, when k is 0, and we'll put the vectors on here now, h1 tangential is equal to h2 tangential. So now in this case, we see that the tangential component of the magnetic field intensity is the continuous one, and then based on how it's related to the magnetic flux density, like this, we see the tangential component of the magnetic flux density is discontinuous. It undergoes some change. Now, let's bring in some angles into the picture. Let's call this thing theta 1, and by vertical angles from geometry, that's also this angle. And let's call this thing here theta 2, and again by vertical angles, that's also this angle here. Theta 2. Yeah, we'll just call it. So theta 1 and theta 2 are the angles that B1 and B2 respectively make with the normal of the interface. So now if we can find the components, we can say that B1 normal, and without the vector here, so this is just the magnitude, is B1 times the cosine of theta 1. And we said that that has to equal B2 normal, so that has to equal B2 cosine of theta 2. Similarly, based on this here, the tangential components, B1 sine of theta 1 over mu 1 must equal B2 sine of theta 2 over mu 2, like that. Now, if we divide the two expressions and rearrange things a little bit, so if we divide this expression here by this expression here, then we have sines over cosines, and the b's drop out, and so what we get, let me give you some space here. So sines over cosines is tangent, and the b's drop out, leaving just the mu's, and we get, lo and behold, this thing here, tangent of theta 1 over tangent of theta 2 equals mu 1 over mu 2. Nice. That is Snell's law of refraction, but for magnetic fields. Alright, so I think I have some examples coming up, and then after that we're going to get into inductance. So I will see you then. Thank you.